Hello, this is Jack Jackson. In this video, we're going to talk a little bit about Fermat's last theorem and its ultimate proof by Andrew Wiles. You see Fermat there on the left and Wiles on the right. I want to give some credit to my friend and colleague, Dr. Todd Timmons, who this video is really based on closely based on some slides that he had for a similar lecture earlier. So, Fermat's last theorem. Pierre de Fermat, in the margin of his copy of Diophantus Arithmetica, wrote this interesting statement. Translates as, but one cannot split a cube into two cubes, nor a quadriquadrate into two quadriquadrates, nor in a general any power in infinitum beyond the square into two like powers. I have uncovered a marvelous demonstration indeed of this, but the narrowest of the margins will not contain it. So in modern language, this would say, or notation, it would say x to the n power plus y to the n power equals z to the n has no integer solutions for natural number n greater than or equal to 3. So in other words, if you take x to the third plus y to the third equals z to the third, um, then there are no integer values of x, y, and z, well, natural number values at least, that would make that work. Easily stated theorem. Okay, it's understandable to elementary school students, but it's extremely hard to prove, and it generates much new and interesting mathematics. So this is kind of a remarkable thing because, like I said, you can, as soon as a elementary school kid understands what an exponent means as repeated multiplication, and they can understand basically substituting in variables, you can explain this theorem to them. But yet, it's extremely easy to say, but it's very, very hard to prove. And so this actually generated a lot of amazing mathematics. Now, we know when n equals 1, there's lots of solutions to this. And when n equals 2, there are also infinitely many solutions. For n equals 2, they're called Pythagorean triples. For example, the smallest Pythagorean triple is 3, 4, 5. 3 square plus 4 square equals 5 square. 3 square is 9, 4 square is 16, 9 plus 16 is 25, and that's equal to 5 square. Fermat claimed that there are no integer solutions when it's 3 or 4 or any higher power natural number. Okay? Or no, I should say natural number solutions. Now, why did he get the name Fermat's last theorem? Well, it's not necessarily because it's the last one he came up with, but it's because it's the last of his many theorems that to be proved. And it is interesting that because of this cryptic statement that's in this margin of this book that he had, and the pursuit of a valid proof has engaged some of the best mathematicians of all times, and it's produced significant new mathematics. And it all came from this rather simple statement. It's pretty remarkable. Now, it's actually highly unlikely that Fermat ever actually had a valid proof. He often never got around to writing up complete proofs of all his work, and sometimes later mathematicians would prove it and finish writing them for him. It is likely that he had some insight that the theorem was true. He had an idea that he thought would lead to a proof, but labor was unable to turn that into an actual proof, or just maybe never get around to following through with it, the whole thing. So really, it probably shouldn't be known as Fermat's theorem. It should be known as Fermat's conjecture. See, a conjecture is a statement you think is true, but you haven't proved it yet. Once it really doesn't become a theorem unless somebody provides the proof. Okay, so even though it's called Fermat's last theorem, again, it probably should be called Fermat's last conjecture. Now, many prominent mathematicians, kind of a who's who of mathematicians, have made attempts at a general proof, and many of them made some significant advances, sometimes proving certain cases, sometimes making some headway. For example, here's a partial list. Euler, Gauss, Abel, Germain, Legendre, Dirichlet, Lebesgue, Louisville, Cauchy, Jacobi, Lamé, Hilbert, uh, Dedekind, Wronski, Kummer, and many others. So there are lots and lots and lots of really important and famous mathematicians, some very, very, very brightest guys, some of the smartest guys in history here, and guys, men and women, that worked on this. Um, and uh, None of these people were able to actually prove this in general, but some of them made results. So, for example, Euler was the first one to really make some serious headway, and he proved Fermat's last theorem if n equals 3 or n equals 4. And he's really the first one to give a proof for any of these cases. You may recall Euler is definitely one of the handful of greatest mathematicians of all time. He published more stuff than just about anybody. Sophie Germain did a lot of important work on Fermat's last theorem, and her work led to establishing a theorem for a certain class of prime numbers, but she didn't actually prove that prove the whole thing. Legendre proved proved it for m equals 5, and Lamé proved it for n equals 7. So in the early 1800s, proofs were worked out, but only for some specific cases of n was n small. So we've got it proved for case 3, 4, 5, and 7, some of the smallest cases. And then comes along Kummer. Ernst Kummer proved the theorem for a class of numbers called regular primes. He showed that the theorem holds for all prime exponents between 3 and 100, except for 37, 59, and 67. So he was able to work it out for lots of different prime powers. So it had taken 2 centuries to accumulate proofs for the n equals 3, 4, 5, and 7, and that at once Kummer had a proof for many of the other values up to 100. This was a huge step toward a general proof as well. By the start of the 20th century, various techniques in number theory had been created in part to solve this problem. In fact, many things, much number theory had been developed by this time, and a lot of it had been generated by interest in this particular problem. So using these techniques that were around and then high-speed computers, the theorem was checked and verified for values of n up to 150,000 by 1987, up to 1 million, n equals 1 million by 1991, and up to 4 million by 1993. So by 1993, we knew for sure that the theorem was true for n equals 3 up to 4 million. Well, is that enough proof? And the answer is absolutely not. No matter how many cases are proved, until a general proof is produced, it still remains a conjecture. And let me give you an example of why this is the case. Why do mathematicians insist on a general proof, even if they work something out up to 4 million examples? Okay, so here's another example, and it's related to the Fermat's last theorem. Euler had proved that x to the fourth plus y to the fourth equals z to the fourth had no natural number solutions. Okay, but what could he do next? Well, one of the things you can do is generalize. When you have a problem in mathematics and you can solve it, sometimes that's the very best time to work on a problem to see if you can solve a similar problem. So in this particular case, what Euler did, he says, well, let's look at this. Let's look at w to the fourth plus x to the fourth plus y to the fourth equals z to the fourth. I bet that doesn't have any solutions either. I know if I just add 2 to the fourth powers, we can't get a fourth power. But what if we add 3? And so Euler made that conjecture, and that conjecture was believed for at least 2 centuries. Everyone believed that Euler was correct. But then somebody finally came up with a counterexample. All it takes to prove something false is one example where it messes up. And they found an example where this equation could be solved. The smallest solution turns out to be WXYZ equals, the W is 95,800, X is 217,519, Y is 414,560, and then Z equals 422,481. So notice they had to get pretty big numbers for this to work out. Of course, I suspect there are a lot of other solutions, but they're all going to be with numbers even bigger than that. So just because it worked for the first, numbers up to, over 95,000, for all the numbers, uh, doesn't mean there can't be one even bigger. So this is why why mathematicians insist on a general proof. No matter how many cases we could work out, we don't know for sure that there might be another one later on down the line. Of course, working it out for 4 million cases, for n up from 3 to 4 million, gave us a pretty good idea that's probably true, but it was not proved. Now, probably the most important thing about Fermat's last theorem is not the theorem itself, but the search for a proof ended up creating much new mathematics in the field of number theory. Turns out that there are a number of results in number theory that are related to Fermat's last theorem. A study of elliptical equations in modular forms, apparently far removed from the original conjecture, turns out to have a lot to do with the proof. Goro Shimura and Yutaka Taniyama were two Japanese mathematicians who in the 1950s conjectured that there was a relationship between elliptical equations and modular forms. Later, thanks to the work of mathematicians Gerard Frey, Ken Ribet, and Barry Mazur, it was shown that the Taniyama-Shimura conjecture Taniyama and Shimura. It was shown that the Taniyama-Shimura conjecture implied Fermat's last theorem. So if they could prove the Taniyama-Shimura conjecture, that would mean that Fermat's last theorem was proved. And this was the approach that Andrew Wiles ultimately used to produce a valid proof. So let's talk about Wiles just a little bit. He was born in 1953, and as of this recording, he is still alive. He's English. He became interested in Fermat's last theorem when he was just a schoolboy at King's College School. So, as I've said before, you can explain the theorem itself to a fairly young child, and it's fascinating, and it fascinated Wiles, and he became somewhat obsessed with trying to be the one to prove it, although he wasn't the first one to try that. In 1971, he entered Merton College in Oxford. He got his bachelor's degree in 1974 there. He went to Clare College, Cambridge, and completed his PhD under John Coates. He worked at Cambridge and Harvard from 1977 to 1980, and he finally completed his doctorate in 1980. In 1982, he went to the Institute for Advanced Study in Princeton. That's where he worked there. And he worked on a variety of topics from number theory. But then when he heard this thing about the Shimura-Taniyama conjecture being enough to show that Fermat's last theorem was true, he thought, hey, this is an approach that could work. This is an approach that he could actually do. So he basically worked on this in secret by himself for 7 years. He basically abandoned work on other things for the most part and spent 7 years really concentrated on proving this Shimura-Taniyama conjecture. Well, in the summer of 1994, Wiles gave a series of lectures at a conference in Cambridge, England. And as the lectures went on over a series of 3 days, There was more and more excitement building in the room because the people there could see where this might be going. By the third day, the room was packed. When Wiles reached the end, he said, "Oh, yeah, by the way, Fermat's last theorem has now been proved to be true." He stopped the lecture there, and the crowd went wild. They erupted in a standing ovation. He had solved a centuries old problem, and he had used the latest cutting edge uh, number theory to do it. But wait, there's more. A result in mathematics is not fully accepted until it has been carefully peer reviewed, verified, and published in a respected journal. During the process of getting it ready for publication, Wiles found that there was an error in one section of this very long and difficult proof. Now, he had done enough work that a lot of people that were really experts in the field were pretty convinced that he at least had the correct approach, but it was turned out to be very difficult to patch this hole in the proof. But finally, he enlisted the help of one of his former students, Richard Taylor, and together they were able to make the necessary corrections. However, these corrections took over a year to complete. In 1995, the final corrected version of the proof was finally peer-reviewed and published. At last, after centuries, a valid proof for Fermat's last theorem. Well, Fermat's conjecture, probably we should call it Wiles' theorem now, had been published. Wiles has subsequently been awarded several prizes, including the Abel Prize, one of the two most celebrated prizes in mathematics, and he's even been made a Knight Commander of the Order of the British Empire. So, Sir Andrew Wiles has proved Fermat's last theorem. This remarkable story of Fermat's last theorem illustrates how a simply stated conjecture can sometimes lead to remarkable results and even the creation of entire branches of mathematics. Huge areas of number theory were created, in part inspired by this particular problem. And many advances were made by various amazing mathematicians working on this problem, even by the ones who were not able to make a general solution. Now, it's highly unlikely that Fermat actually had a valid proof, even though he said so in the margin of his book. Considering the vast amount of mathematical knowledge that it took to provide the published proof, and the fact that these modern techniques were obviously not around back then, and the fact that we've never seen the proof attempt of Fermat, I think most mathematicians and math historians will say that yeah, Fermat probably didn't actually have a proof. That doesn't mean he was lying about it. It just meant that he was, a little bit overzealous in stating what he thought was the proof. I'm sure he probably looked at it and could see some math. He could see some intuition that this probably was going to work, and he thought he had a technique that would work. But then later on, either he examined it and and wasn't able to make the proof work, or and he realized it, or he just thought this method that he had in his head would work out, but he never got around to actually working it out. But either way, that's probably what happened. Or it's possible he wrote something down for a proof, thought it was correct, and we just never have found it since then. But we have no evidence for that. So what's interesting is how much that this has fascinated mathematicians for centuries. And even though the problem is solved now, further work can continue on the problem. For example, one could look to see if it can be proved by other methods rather than the method that Wiles went at it. Others might work on generalizations like the one that Euler tried that we talked about earlier, or other related material. So oftentimes when you get a problem solved, that just opens up even more interesting mathematics that can do later. And some of the tools can and have been used since then. So the work that Wiles did, actually he proved a limited version or of this conjecture, And so there's work on trying to prove the full conjecture. There was work on using the tools and the techniques that Wiles made use of in his theorem to work on other problems. So there's all kinds of things that can come out of working on some mathematics. And in this case, a little note in the margin several centuries ago has inspired lots of cool mathematics.